In the late 1700s, the French physicist Charles Coulomb studied the interaction of charges. Now, we may be more familiar with magnets or gravity than we are with charge, but charges behave in much the same fashion. Now, with gravity, there's a force. If I think about this shirt, there's an attractive force of gravity between the center of the shirt and the center of the earth. But there's also an energy associated with this scenario. Right now, the energy is a potential energy based on the position of the shirt. But if I let go, the potential energy is converted into kinetic energy. Now, gravity is only attractive. Both magnets and charges are more complex because they can have attractive charges or repulsive charges. Having a way to quantify the force and energy when charges interact will be very important for us. If you saw the magnet demonstration, you know that the forces between magnets depended on the size of the magnets as well as the distance between them. The same is true for charges. Instead of north and south with magnets, we consider positive and negative charges. This language was supposedly introduced by Ben Franklin. Coulomb first studied the interaction of charges and how the force depends on the distance between them. The modern relationship for force, given the symbol F, looks like this. Q1 and Q2 are the charges in units of coulombs. R is the distance between the charges in meters. Epsilon is the dielectric constant, sometimes called the relative permittivity, of the medium and would be unitless. The medium is the material that is in between the charges. Epsilon is a measure of how well that material insulates the charges from one another. In a vacuum, there is no insulating effect and epsilon equals 1. K is a constant which has a value in Newton meters squared per Coulomb squared. Physics tells us that the force and potential energy are related by a factor of distance. So for interacting charges, the equation for force and the equation for energy look very similar. Note that force has r squared in the denominator, while energy has r to the first power. We are not going to use these equations to calculate exact values for force or energy. Rather, we will use the relationships to compare the forces and energies of different scenarios. We are most often interested in what happens to the energy when the charges change or the distance between the charges changes. To make those comparisons, we can use a simplified version of Coulombs law. Energy equals Q1 times Q2 over R. While this won't give us energies in traditional energy units, remember that we will be comparing scenarios, so the actual units don't matter. In chemistry, we refer to charges simply as integers, rather than their true values in unit of coulombs. But there are a few things to take note of. Charges can be positive or negative, so we need to keep track of sign. Distances will always be positive. We will talk about like charges, where the signs of Q1 and Q2 are both positive or both negative. Like charges doesn't mean the same number, just the same sign. Notice that will result in a positive value of energy. We will also talk about opposite charges, where one is positive and one is negative. That will result in a negative value of energy.